is a new self-adaptive composite we made in the Department of Material Science and Nanoengineering.
So basically, all we have to do to show you kind of the interesting properties of the material is we cut once. You can see we have one piece here. We cut again. Now we have two pieces. And what's interesting about this material is that because of the way it's structured, with all the spheres and the liquid phase, we can actually have these two pieces become one just by pressing. So now I will stack them on top of each other and just compress and get a single piece.
The original thought was putting the liquid inside the solid matrix, but we want to introduce more flexibility and adaptability of the material. So we want to introduce more liquid. But the problem is how we hold the liquid inside the composite instead of let them flowing everywhere. So what we did is we choose the two elements which can form the weak bonding to each other, and then helping them to keep in a solid composite, look like a solid composite. After the testing, it shows the self-healing under tension and also self-stiffening under the compression. So also this is only a demo of the material which I just showed, and it can be tuned. The storage modulus and also the morphology, everything can be tuned due to the playing with the procedure and parameters.
You don't really expect something that's half liquid, half solid to even hold its shape. It's kind of a misnomer. You think of, well, it's half liquid. You think of something like Jello or something a little bit different. In this case, we have no flow. As you can see, it's actually, pretty rigid to the touch, and you have to actually squeeze quite hard for it to deform. The fact that we can mold it by changing the processing techniques and saying, hey, I want it harder, I want it softer. You can't do that with Play-Doh. It's a little hard. Play-Doh, you can change temperature, but you can't really change anything else.
That was also a great invention, to be honest, and because everybody use it and play it. But the good part or the normal part we were thinking of is you have to use a microscope. You can see the internal structure. They can move. There is an external stimulation, and the internal structure can rolling and rearranging itself to adapt themselves to the external force. And even more, if you apply such a large force, and then the two spheres can merge into one. So it's really like they're communicating to each other, see, hi guys, how can we do it better? And to fight with the external force. So we think that's smart materials.
Because of the way it can adapt, it can fit into different roles. Depending on how high we can actually scale the strength, we could see it possibly used as building materials. But more likely, it's very interesting that we see this kind of stiffening ability. The fact that the stiffness can become higher is actually quite interesting, and that's kind of one of these self-strengthening mechanisms that you could probably see in the future.